Hi, this is Terry Kuzma at Penn State University. Today we'd like to go over materials and nanotechnology. This is the introduction to nanoparticles and nanostructures. So what we're going to do is define, look at some definitions and examples. And so we're going to look at the physical size and properties of nanoparticles. Later in the lecture, what we're going to do is look at the optical properties in part 2. So let's go ahead and let's define what a nanoparticle is. So it's a structure with at least one dimension less than a micron. So we can have examples of this like sphere-like particles, which we can see as, which are common, or things like silver nanoparticles or buckyballs. We can also have rod-like particles, which could include silicon and nickel nanowires, and then tube-like particles, which could be carbon nanotubes or titanium dioxide nanotubes. So let's take a look at material properties. What do we see? We see that with gold, we would measure properties on the bulk scale, and no matter when it's large or very large, the resistivity, melting point, and optical absorption would be the same. But when we look at gold as a nanoparticle, we would actually see that it's no longer the color of gold. It can change, the color can change, and the color can change in a couple ways, certainly by the diameter, but also due to the shape of the nanoparticle in that, as the shape, and then depending on what medium it's in. So these are all, I don't know if these are all gold. I think it's gold and some are silver. But these are actually different nanoparticles, and what happens is they interact with the light differently. So now what we have identified is the optical absorption is different on the nanoscale. But interestingly enough, when there's different optical absorption, because we're on the nanoscale below 100 nanometers or so, the melting point, the melting temperature is going to change also. So will the relative resistivity of the material, so will the bioreactivity of the material, so will the magnetic properties of the material. So when we are on the nanoscale, the vision that I like to always think about is, on a standard periodic table, you have melting temperature, et cetera, of all these different materials and different material parameters. When you're on the nanoscale, that it's a new periodic table. So let's take a look at some physical properties. So what I define, first of all, what would I say a nanoparticle is a quick description. I would say that it has a very large surface to volume ratio. And that's important because really interaction of most material happens at the surface. So what we're able to do is when we maximize the surface to volume ratio, we can reduce the amount of material that we need for a particular task. I guess a good example of this is if we would make very small particles and put it in a catalytic converter for an automobile, we would be able to use less platinum then. And certainly we can see that as important because platinum is expensive. We would still get the same reactivity out of that material because what we're basically doing, I guess the reactivity is proportional to surface area, not really mass. So what we would do is lower the mass and keep a consistent surface area, and we're able to use less nanoparticle or less platinum when we make the particles smaller. So a high percentage of the atoms, a high percentage of energy for these atoms is on the surface. The surface forces are very important, and we really don't, I guess that they dominate the bulk surface, the bulk forces. Metal nanoparticles have unique light scattering properties, and they exhibit plasmon resonance. And basically what plasmon resonance is, the nanoparticle itself acts like a tuned circuit, and what it'll do is absorb light. That light would oscillate across this shape, and then what it'll do is re-emit that light. So that's an interesting tenet of plasmons or nanoparticles. For mostly metals, they would have this plasmon resonance. Semiconductor nanoparticles might exhibit confined energy states and in their band, and they can also be light emitters such as quantum dots. We can have unique, certainly chemical and physical properties. And interestingly, for medicines, for interrogation like tagging, etc., nanoparticles are on the scale that's used in biological structures, or good for the analysis of biological structures, or good for the use of biological structures. So I guess the basic biological structure is a cell, and cells are many shapes and many sizes. But if I had to give I guess a rough estimate of how big a cell is, maybe a cell is 10 microns. Of course, I'm incorrect, but in most cases, 10 is a pretty good guess. But if we're on the nanoscale, you can see that how much smaller it is to be like 30 nanometers or 50 nanometers compared to 10 microns or so. And in fact, that's the size of the conduits that can go in and outside the cell. So there's different ways the cells can import and export materials, and basically about the size that they would do is on that order below in the nanometer scale, below 100 nanometers. Cells are good at taking material in and exporting at that level. So unusual properties. We have a lowered phase transition temperatures for nanomaterials compared to the bulk. We have increased mechanical strength on average, certainly by mass. We have different optical properties, such as different colors or resonance. We have altered electrical conductivity. Certainly, it usually increases in our case because we'd have more charge on the surface. We certainly have unique metal properties, again, to go along with the charge on the surface. Charged surface in a magnetic field reacts, right? So unique biological responses and unique chemical reactivity of these materials on a nanoscale. So certainly the properties of the nanoparticles are dependent on size, but also on their shape. So the shape could be spheres, rods, or platelets. It's also dependent on their composition. And even at the nanoscale, we can have materials, certain materials could form FCC or BCC basic unit cells. So it would depend on that property too. We can also have the properties of nanoscales could change according to how we would coat the outsides with either some type of ligands or capping agents, so they would interact with the environment differently according to that shell that we might place on there. And certainly the properties of nanoparticles could be dependent on the medium in which they're displaced. Often the mediums that we displace them in are made so that the material, the nanoparticles themselves, don't coalesce together. So we would like to stabilize the nanoparticles so that they don't agglomerate together and lose their nano properties. So if we look at the size of nanoparticles compared to other entities here, we see that for the most part, the number of atoms in a unit from 1 to 10 atoms or so, we would consider that these things are molecules. Beyond that, up to 1 million or so molecules, we would consider the atoms. I'm sorry, we would consider that these materials would be considered nanoparticles, and beyond 1 million or so atoms, I guess we could consider bulk. Again, this is just an approximate number, and like we said before, it might depend on shape if they have unique properties, but this gives us a ballpark number of what we're trying to look at. So if we would look at nanoparticles and define how they would exhibit unique properties because of their high surface to volume ratio, what we could do is we could actually just simply do the calculation here and look at the surface and compare it to the volume. So this gives us, if we would go through this math and do the equations here, if we look at this, this gives an approximate surface area ratio of like 10 million to 1, which is significantly larger than a macro-sized particle. So as the surface area to volume ratio increases, so does the percentage of atoms on the surface, and the surface forces at that point become a lot more dominant. So the general accepted material properties are derived from the bulk, where the percentage of atoms is actually small per unit volume. but these properties change on the outside. And it just makes sense. If you would look at even define or discuss the periodic table, we would define things like group 4 materials because they have 4 electrons on their outer valence shell exposed to the environment. That's how they react. Or if we would look at group 7 materials and say, oh, they're tremendously reactive because that's what defines them, is this outer electron interface with the environment. So basically that's what we're getting in some senses when we're looking at nanoparticle, or at least that's an analogy to think about. So let's here's some sample calculations for surface and volume area, and certainly you can see the trend here. So if we have a nanoparticle and the diameter is 1 nanometer, and we look at the volume, we could say the surface area to volume ratio here is 6:1. But as we go up to, here, this is 3 and 6, that's a million. And so this is the diameter, a million nanometers. And then we would say that that ratio is only 0.000006 to 1. So you can see this dependency right here, that as we make the particle smaller, this surface to volume ratio is inversely proportional. So again, you can take a look at this graph, and this just shows you that the ratio dramatically increases when the nanoparticles drop below about 100 nanometers. So that at 100 nanometers, that's basically why they named nanotechnology. For the most part, most materials below 100 nanometers have unique properties. So above 100 nanometers, those property differences from the bulk begin to subside. But certainly a 200 nanometer particle usually has unique properties, but it's really below 100 to where these things are really measurable or distinct. So let's take again a look at the size. As the percentage of atoms on the surface increases, the mechanical, optical, electrical, magnetic, biological properties all change. So we can take a look at these gold and silver nanoparticles. So actually around 100 nanometers or so, silver nanoparticles appear to be red or whatnot, and gold particles around 100 nanometers. And again, they're the same size then at 100 nanometers. They appear to be orange. And again, these both differ from the parent color. And if we would look at gold at 50 nanometers, we're going to see that it actually appears to be a green color. Silver at 120 appears to be a yellow hue. Silver at 80 appears to be like a blue-green, and silver at 40 nanometers appears to be a form of blue. So again, here's the pictures of these nanoparticles at the bottom, and then the color that they would represent under an ambient white light, the reflection that they would show. So that's interesting that we have, well, it's nice that you could see that through this color range, by using nanoparticles, we can get different colors, reflected colors from the material, just with 2 different types of materials, gold and silver. So this is the stuff that's suspended like in stained glass windows. And we can see that those windows, have lasted hundreds of years in some places, and they still retain their colors. So one of the reasons that people like to use these nanoparticles for tagging, especially in biological entities, because they don't die out like fluorescent dyes. Fluorescent dyes have a half-life associated with them to where they no longer fluoresce, and that depends on the particular fluorescent dye that you're using. But these nanoparticles, as a plasmon per se, their light emission is for a super long time, lifetimes. So this stuff is a lot better in some cases than the fluorescent dyes on that scale. So we can also take a look as an example, a classic under the nanoparticle discussion is the melting point as a function of particle size. And we could see on the list down below that's in angstroms that we could see that below 100 nanometers or so that we have a different melting temperature. So we critically look at when we make nanoparticles for catalysts to make nanowires. We often run our recipes around 400 degrees, 500 degrees to actually get the gold to melt at that point. So that's the size of the nanoparticles that we're using. And gold melts at, I don't know, standard gold, I think, it melts over 1,000 degrees. I forget the name. 1064 maybe gold melts at. So comparing to 1064, no, it'd have to be more than that, because here's the bulk number. I forget what gold melts at, but anyhow, when we're here below on the nanoscale, it melts at a lot lower temperature. So most solids are crystalline with their atoms arranged in regular matter, regular repetitive manner. This arrangement of atoms impacts the functionality of the material, certainly. Some solids have this order presented over a real long range in a crystal. Amorphous materials such as glass or wax lack long-range order, but they can have a limited short-range order defined as the local environment that each atom experiences. So we'll take a look at this. The crystal structure itself, this is the spatial arrangement of atoms in a crystal lattice as described by a unit cell. The unit cell is the smallest possible volume that displays the full symmetry of the cell. Many materials have a preferred unit cell. So on a periodic table, we can identify certain materials, and we would know that they would have per se a preferred unit cell under equilibrium conditions. So the crystal structure itself could be defined by 3 lattice constants and 3 angles. And if you did the math and then you would change these uniquely, we can get 14 possible combinations. So we would call these the Bravais lattices. So these would have different shapes. So there's a limited amount of shapes, and materials would come into these shapes. So for standard a cubic cell, there's 3 centering types. The simple cubic that only has atoms on the corners, the body center cubic that has them on the corners and also one in the center, and then the face center cubic to where we have the corners populated and also the faces are populated by atoms. So when we take a look at the closed pack lattices and identify their general geometries, we can look at face-centered cubics, and the material that naturally occurs in that would like to form in that face-centered cubic position is, silver, aluminum, copper, cobalt, lead, platinum, and rhodium. And if we get HCP, they're defined by these metals here. And then, interestingly, if we look at chrome, lithium, strontium, that they can form BCC, FCC, or HCP, and this is dependent on the formation energy that was given to them, so they can actually go into different shapes. And I guess we see this when we look at per se or understand it and analyze things like phase diagrams, that we can see that there's different properties within these phase diagrams and different formations and different materials such as steel, etc. So how do crystal structures impact nanoparticles? So nanoparticles themselves on the nanoscale, they have what's termed a structural magic number. And we can define this as the optimal number of atoms that leads to a stable configuration while maintaining a specific geometric structure. So a structural magic number is a minimum volume and a maximum density configuration. So if the crystal structure is known, then we can calculate the atoms to give these structures. So we can take a look at the mathematics here that's been reported in the journals and in text. We can look at a particular structure and then look at the number of shells and the number of atoms in a cluster and then the percentage of atoms. At this period, when they're at this balance, that they actually have the maximum surface to volume in this particular geometric shape, this is when they exhibit the most unique nano properties. So this is the most energy per volume for a given mass. So if we would add one more atom to this per se, it wouldn't be at a maxima for us. So I always picture these things as per se like maxima, minima in a sine wave. I guess maybe because I'm an electrical engineer and we like to model things with sine waves, you know. So, but I always look at this as a nodal property that when we get to this certain size, then we're going to have these special attributes. And certainly this is easy to calculate mathematically, but you can also see this qualitatively. So they can, you know, people study these particles, analyze these particles, and just as the mathematics predicts, these materials are actually energetic at these particular sizes. So again, here we can do for n number of layers in an atom of an FCC nanoparticle, we can use this formula to derive the number of atoms on the surface. So this is, again, just doing the math for you to look at the shell number, the diameter, and the percentage of atoms on the surface. We can take a look at this and show this relationship of the high energy and where these things are at maximum. So again, these things are calculated, but they're also shown to be true in the measured sense qualitatively. So now we'll take a look at, you know, I guess a detail of crystal formation. Wulff crystal shapes are predicted shapes. They're used to determine the shape of a crystal when formed under thermodynamic equilibrium conditions. So we'll define this as, or look at this as, the surfaces have a high surface energy, and different facets will actually have different surface energies. So the object here is actually to, or what nature does is to minimize the total surface energy on a crystal. So this is how crystals are formed. So again, these show the plots here and basically how the facets would grow according to their geometries. In this notation, we're using the Miller indice planes to describe this particular attribute. So again, here's the Wulff plots. This shows the proportionality of surface energy to the facet, and it shows that how these crystals would grow for us. So when we look at actually, you know, I'm saying in the real world, but under non-equilibrium conditions, what will really form. So nanoparticles are often formed in this non-equilibrium state, so they don't form well-defined crystal facets. So the Wulff crystal shapes, again, are idealized cases where the crystal energies determine the shape under thermodynamic control. So kinetic factors often play a role in crystal growth. This explains why different processing conditions can lead to different morphologies, even for the same material. So we need to define the roughening temperature as above this temperature, the surface of the atoms growing on a crystal have increased mobility, and they act like the surface is liquid-like, and at this point they don't form well-defined facets. So they would have things that feature curvatures instead of more linear growth rates. At elevated temperatures, all faces tend to have similar energy, and we can look at this and consider certainly the Chagallsky process for growing silicon. So we also have to define, like, when we take a look at surface energy and the interaction of atoms with the environment, we have to model or see or determine the energy between the material and the interface. So mathematically, if we would look at an original structure, we would define that you know, the spacing in the lattice, if it's a single crystal, is, you know, I guess on the order of 10 to the minus 10 meters or so, and these are equidistant. But in reality, what happens is the bulk atoms are sharing energy with their nearest neighbor, so that distance is equidistant. But at the surface, that there's dangling bonds. These bonds don't have some way to be tethered or to share their energy. So what they do is they reach down into the bulk. So at that point, what happens is the surface bonds become to be shortened. So the first, atomic layer, that distance between atoms is actually decreased. We can also have at that surface, certainly under even non-equilibrium conditions, maybe under heat or some other energy stress, actually the bonds can shift on the surface. Again, this is to better share the energy at the top. So what they're doing is trying to use or satisfy their bonds in that fashion. So when we take a look at the nanoparticles, we can calculate the mechanical strength. So for idealized crystals, we would take a look and see that the strength is a lot different than we would calculate. There's certainly a difference between nanowires and nanocomposites, and a transition strength that most people would identify is about 10 microns. So this is where we would say that these small particles would exhibit really high mechanical contribution to materials like composites. So there's a couple of possible reasons that are true across the material. There could be a lower number of defects inside of nanowires, and then certainly fewer surface defects on these nanomaterials. So what we'd like to do now is prepare for the next lecture. So what we did is we took a look at the defined and gave some examples and physical properties of nanoparticles. The next time in part 2, what we're going to do is take a look at optical properties, certainly surface plasmons and quantum confinement. We'll do that. We'll do a quick job over that because the other courses within our program are going to look at these in a lot more detail. I just wanted to give a quick overview here. And then we'll move on with some other material. So I'd like to thank you for your attention during this presentation and look forward in part 2 of our discussion on nanomaterial properties.